Hello. Good afternoon. My name is George, and I've been working at Uber in the past few years. Today, I'm going to share with you one of my recent journeys of building big data and AI-driven solution for Uber. And some quick fact about the company. Uber is a global technology-driven ride-sharing company. Since its launch at 2008, it has rapidly grown to today's 600 more cities. We proudly partner with over 2 million active drivers. And on this platform, we do more than 10 million trips every day. And in recent years, Uber also launched a separate business line, which is food delivery. It covers from fast food chain like McDonald's to your favorite local restaurant. And we have more than 40 million monthly active riders on the platform. Now, this talk is about money. So money-wise, in last year, the gross booking exceeded $20 billion. You can imagine that managing finance at Uber is a challenging job, given the scale, the size, and the rapid growth. There's a lot of decisions to be made about money, about investment, and about growth. And these decisions are usually strategic and very critical to the business success. And whenever there's a brainstorm about how do we make decision-making in Uber Finance better, the overarching principle is that we should apply artificial intelligence, big data, and automation to supercharge this process. So this will be the theme of today's talk. I'm going to talk about how, as an engineering team, we power our finance team to make better decisions. And here's the agenda of the rest of the talk. I'm going to give a background information about strategic finance decisions. What are these decisions? Are we talking about? Why are they important? Why are they made? And then we're gonna talk about how engineering roadmap is brought into the picture, and what are some essential elements, the high-level software architecture, the selection of technology, and the tech stack. Hope I don't bore you too much. And then we're going to dive into an actual use case. Earlier this year, we built an app and delivered it to our finance team for their use in forecasting and planning. I'm going to dive into some detail about what that tool is and how exactly is that helping the users and some of the benefits. And along the way, I'm going to highlight some interesting work that my team does. All right, so this picture shows an example of a financial operation cycle, and we're going to walk through it and see what kind of decisions we make during this cycle. You can see there are 4 phases. They're connected, and they form a closed loop. And of course, this is not the only way that we can interpret an operation cycle, but at Uber, we found this pretty representative and typical. So the box on top, you can see is strategic planning, and informally, you can think of this process as making the big decisions. And this phase usually involves the leader of the business, and usually it's a small group of people make really high-level decision. And the outcome of this phase is priority of the company, high-level investment strategy, the focus in different geographic group, and so on. So in this phase, we'll make the decision, for example, how should we invest in a group of cities, right? What should be the priority? What should be the growth target of this country? And how do we get there? Is it possible to get there? In terms of Uber ride sharing, should we focus on the supply side, which is the driver, or the demand side, which is the rider in a given market? And these are very challenging questions to answer. And then once we have the high-level strategy set, we move on to the next phase, which involves more people, but we make more detailed decision of a smaller scope of the business. So this phase is usually referred to as allocation and guidance. And in addition to the business leader, there's also the regional leader or the Uber city manager participating in this phase. And this phase fine-tunes the plan, as well as making adjustment based on the strategy, based on the special insight that the city manager may have to their special city. For example, we may ask, what is the impact of giving certain money in rider promotion in the city? Right? How many more rides will that bring? What is the effect of reducing the price, right? Or just simply, how many trips will this city see in next year? And after that phase, we have a pretty detailed plan, a forecast, as well as the allocation of the budget in the system. And moving on to the next phase is all about monitoring when the business is in execution mode. And in this phase, we collect a lot of metrics, we analyze them, we show them to the headquarters as well as the city team so that they can monitor the growth, the trend, the progress. And this very last phase is usually neglected, but it's very important, which is once we have the execution data, once we have the actual performance metric, we look at that together with the plan or with the guidance, and we gain a lot of insights from comparing them. For example, if there's a discrepancy between the forecasted growth and the actual growth, we want to figure out why. Is our forecast inaccurate, or is there some signal that we're missing in the plan, or we're using a wrong strategy to do the planning? Or if there's some action that needs to be taken to, for example, catch up more transactions, catch up more signups, we want to ask what is the best way to do that. So you can see these are the questions. These are interesting questions to answer. And another way to look at these questions in a more systematic and data-oriented way is bring in the timeline and the horizon. So here in this two-dimensional graph, you can see the y-axis as the timeline. So think about a year, and every row is a horizon in a given month. And every column is 1 month in that horizon. And of course, depending on where that month is, part of the horizon will be the future, part of the horizon will be the past. And we can map those questions that we saw on the previous slides to this diagram. For example, let's look at the very bottom row in January, or even before this year begins. Then we're looking at the whole year. It's pure future, right? And we want to solve two problems. We want to solve the optimization problem that come up with a optimal budgeting plan for the next year. And along with that, we have the initial forecast of what the business will look like in the new year. And after that, if you move up, you see the orange pinky problem. It's called rolling strategic forecast. Every quarter, we reforecast the rest of the year. As you can see, in Q2, we forecast 9 years. In Q3, we forecast 6 years. And in Q3, we forecast the rest 3 months. Sorry, 3 months. And almost all companies do that. In fact, public companies are required to do that and to give a guidance to all the shareholders. And another related problem is the short-term forecasting. And you can see the purple problem that happens much more frequently. It can be every month, it can be every 2 weeks, every week. And the goal for that problem is to look at the near future and look at the growth trend. So the difference between short-term forecasting and rolling strategic forecast is usually by default it doesn't involve reallocation, or think of it as a read-only forecast, if you will. And these are the problems that involve looking at the future in the horizon. There are also important questions that's about the past. For example, if you look at the left, there's a model testing problem. In a given month, say in August, we've seen 7 months of actual data. Now, we want to run an analysis of our model, of our forecasting model, to see whether they're still accurate. We want to validate whether our way of seeing the future need to be corrected as we go on. So this is model testing, or back testing in some literature. And then we also have this blue-color performance analysis problem. This has to do with comparing the actual performance with the forecast and figure out the discrepancy and try to explain the discrepancy, try to come up with the corrective actions, recommendations, and so on. All right. If that's not interesting enough, remember Uber runs in 600 plus cities, and every city is different. A forecasting technology that works, that produces very accurate result in Paris may or may not work in Singapore. We may need a different model, completely different model, or we may need a different set of hyperparameter. And also, Uber runs different product line. Optimization technology that works for food delivery may or may not work for carpooling. So we have this two-dimension of complexity, and we're solving this problem at a pretty large scale. We used to have a human process to solve these problems with, the assistance of spreadsheet software, proprietary software, and some basic automation. And even with that, you can imagine it's very hard to catch up with the growth of this two-dimensional scale. And the question we then naturally ask is, how do we teach machine? How do we build system that help us answer this question? And you can imagine if we have a large enough LED display, and then we build a machine that can pop those answers to the screen. We put that screen on the wall. That makes a pretty good, robot financial advisor. Now, with that mission in mind, what kind of engineering solution is needed? And let's talk through some of the essential elements. Of course, first of all, we need data. Without data, there's nothing that can be done. And what's special about financial data is that they are created from different systems. They come from different places. For example, if an Uber trip finishes, we generate fare, a trip generates fare, and then it goes through the payment system and disbursement system to settle that transaction, and then you have the fare in the system. On the other hand, if the company hires someone or if the company purchases equipment, that data is probably come from the corporate system or a third-party accounting system. And the two systems may not even connect to each other. So it's challenging to aggregate all this data related to money in the same place and provide access in a unified way. This is why we built a special financial data warehouse. And on top of that, we need a solution that allows us to specify metrics and their dependency, their relationship, as well as the way we compute the metrics. And essentially, it gives us a way to formulate a business problem to an engineering language that engineers can understand. And of course, we need a machine learning platform. And we built machine learning model as a very essential element in the engineering solution. And I mentioned forecasting model a lot. Forecasting is one of the most important models we have to build. But also, in addition to forecasting, there's also models that tell us the relationship between the metrics, that models that allow us to derive one metric from another. These are all the application domain for machine learning. And it's not about all learning. There's also general computation, composition of the model, experimentation of different ideas, backtesting of the model, and so on. So we need a generic compute framework that we can run our almost arbitrary workload. And last but not least, we need an interactive application and data dashboard to get people involved in this process. We would very much love if our AI is perfect, just like AlphaGo or AlphaGo Zero, that doesn't require any human intervention, just come up with a perfect plan. And all people need to do is click and say yes. It's a long-term goal. For now, the realistic plan is to have AI and human together answer these questions. So we need an interactive application. Now, if we map all these to a layered software architecture, this is almost a repetition, but I'll just go over it. At the bottom, you have different kind of data source. You have the production service. We have over 1,000 microservices in Uber. Any one of them can generate a money-related metric that need to be monitored and collected. We have our corporate system, which is disconnected from the production services. We have a lot of third-party services used by the finance team, and we also have metadata to maintain. But moving one layer up, once we have this financial data warehouse, you have unified structure, storage, as well as API to access this data. And on top of the warehouse, we build two things. We build a transformation, a pipeline manager that allows us to specify data transformation, and we also disperse the important metrics to an online store so that we can access it much more frequently with much lower latency to fit the need of the application. And on top of the data layer, as I mentioned in last slides, we have a machine learning platform side by side with a generic computing container that we can run workload on. And moving one layer up, there is the scenario management system. This is where we define the problems. This is where we define a set of metrics as well as their dependency as well as the goal that we try to solve. We're going to see some concrete example of this, by the way, later in the talk. And at the very top, we have the dashboard. We have the interactive planning UI that all the finance team as well as our city manager, our operation team use, the forecasting UI, and some admin console. So when we build this, we learn some important principles. And quite honestly, we didn't know them before building them. So many of these principles are, in fact, learnings, or at least reflection. I like to just highlight them in case they're useful. Number one, the platform needs to support model customization. It would be ideal if we build a platform that we can import an algorithm or a machine learning model from the library and just work. But in reality, it seldomly does, because finance is such a special field that almost all the standard model and algorithm need tweaking before it can be applied. And second, we need to provide a flexible entry point to the system. The system needs to be configured to do on-demand problem solving as well as periodical problem solving. There are different use cases, but equally important. And third, the system needs to handle bursts of workload. Typically, when we think about planning and forecast, we were confident that we can schedule the workload or we can amortize the load so that there's no spike of load. But in fact, we sometimes have to respond to business changes, environment changes, or the sudden need of recomputing a lot of things and regenerating a lot of, re-answering a lot of questions. So that elasticity is much needed, especially in the compute framework. And the next one is also interesting. We should be able to separate the AI, the detail of the AI algorithm of the model from the end user. A typical example is when we forecast. The forecast algorithm works best with a certain cadence. Some algorithms work best when you do monthly forecast. It doesn't work that well when you work with weekly or daily. But when you deliver the result or deliver the decision to the end user, to the business user, they have their own cadence or schedule of doing things. For example, if the business plans on weekly, then no matter what your forecast model is, the engineering solution in the middle has to provide the value of converting back and forth so that the business doesn't need to change as you swap a different algorithm. And similarly, we can swap a different model, a different algorithm, a different optimization without necessarily changing the interface. And last but not least, we need to provide a feedback loop. The system needs to be able to generate feedback based on human input, and in case we need to use that to iterate our algorithm and intelligence, we have a way to do so. We don't lose any human intervention from this platform. All right, I hope it's not so boring. Let's quickly look at a realistic tech stack of what we're actually building. I think in order to present it clearly, I separate the components that participate in the offline workflow, which involve model training, preparing the intelligence, preparing the algorithm, tuning the parameter, composing the model, pre-processing the data on the right-hand side, and the online workflow in the left-hand side. So I think there's no surprise. There's no super fancy stuff going on here because we want the system to be reliable, and we don't run our own infrastructure. So we pick the most mature framework, the well-supported software from Uber infrastructure to build this architecture. From the offline world, you can see data training pipeline that connect to the Hive data store on the right bottom corner, and the artifact store, which is the output of the model training, stored in HDFS. There are two types of training. There's large-scale training orchestrated by Spark, and there's also smaller-scale training orchestrated by local compute machine from Mesos. So we do that in order to do easier instrumentation and experimentation. And then the human, typically an engineer or a data scientist, can interact with this system, specify what model needs to be trained, what algorithm needs to be run from a management console with a web interface. Once the data is prepared, the model is trained, we put them in the HDFS store, and it goes through a dispersal process to be moved to an online store in Cassandra. And of course, there you get reliability, you get faster access, and you get all the benefit of an online world. The online world is centered around a management service where the problem is defined and stored, and the computation is orchestrated there. Once we want to orchestrate a compute flow, we either run the model by triggering a model executor, which is proprietary in Uber, or we run a general compute service launcher instance from Mesos, and we store the result in another Cassandra instance called the scenario store. And again, the end user here can interact with the system through a management API by a web app. The user here is not only the engineer and data scientist, but also our finance team and our operation teams. In the online world, we typically do online on-demand forecasting, optimization, and calculating of the metrics. All right, cool. Now let's dive into a real case study, and we're going to talk about an instance that we built, an application we actually built on top of this. The application is called multi-scenario growth planning, and this is the process where we orchestrate budget allocation and give growth forecasts for Uber City. So at the final stage, a city manager of Uber log into the system, interact with the system, and they can come up with a finalized way of spending money, plan of spending money for the next year, as well as a forecast of the important metrics. So he walks up with a plan of his city in the next year. And this process produces a lot of the metrics, such as gross booking, number of transactions, in terms of ride sharing is number of trips, number of active user, and the strategy of spending money. And we're going to see exactly what these metrics are. And this application orchestrates a top-down and bottom-up process in that the AI will generate the initial allocation and the forecast, and we open it up to the user to adjust and to tweak and to see the intermediate result after rerunning the forecast. And once it's done, we approve the plan, and then it go bottom up. You have the aggregated plan for Uber Global. And of course, a lot of the model and artifact need to be built. We need to figure out what are the metrics that's involved in this booking forecast. We need to figure out what model we use to forecast trip and forecast things like fare. All right, so let's look at the problem domain in more detail. So we call the group of metric and model together as a scenario. So these are the things that we consider a unit or a scenario. So the yellow box are metrics, the blue box are models. And the edge is a dependency in terms of computation. So this is a simplified version of what's actually going on in Uber ride sharing, but it catches the majority of the elements. So let me walk through. From the very left, there is the blue box called budget optimizer. With some user input to this box, we generate a spending of the city. And of course, you can see there's intelligence there. There is the spending with a goal in mind for the city, with constraint in mind as well. Once we have the spending, we split the spending into two channels. On the top, you can see this is acquisition spending. This is the money you want to spend to gain new user. And the bottom yellow box is called engagement spending. This is the money you want to spend to give it to the existing user. Now, the acquisition spending is sent into another blue box, another AI, and we derive a sign-up. So we know if you spend this money, how many users will sign up in the system. And subsequently go through another box and come up with the number of the first rider trip and the first driver trip. So this conversion model tells you if you have this many new signups, how many new active users are we going to see? And then on the bottom, the engagement spending goes through incentive model and a chain of models basically forecast trips. And we're going to talk about trips later in this talk. But here you can see we have two models that generate trip. And these two models generate different numbers, and they're sent to a composer. The composer generates a final number for how many trips you have. And then from trips to gross booking is a calculation rather than model. Basically, if you have trip, if you have forecasted average fare, you time the two together, you get booking. And then they go through another models which are technically not part of this flow, and we can generate the flow the inflow after spending. So this tells you the structure, what we considered as a problem model. And these we just put in some concrete number, right? If we spend $200, $100 in engagement, $200 in acquisition, we're going to get, there's a typo, there shouldn't be the dollar sign, 35 new user, and we're going to get 700 something trips, and we got the booking and the inflow. So mapping this back to the software architecture, the blue boxes are models that need to be trained and put into the artifact store, whereas the numbers in the yellow boxes need to be stored in the scenario store. They're both Cassandra. All right, and you can think of this as the initial version. So of course the numbers are all random and faked, but think about the machine going through this acyclic graph in a topological order and compute every metric along the way and store it in the system and expose it to the user. This is the initial forecast and plan. And we allow the user to interact with the system, of course, to adjust the forecast. And the system is smart to figure out what do we need to do after the user edits something. For example, the user may choose to override a metric. It can say, I know better about the sign-up situation of this market than the AI. I think there are going to be 50 sign-ups than 35. So you can punch that in through the UI, and then the system figure out all the models, all the blue boxes in the dotted line, need to be rerun. And they will rerun them with the new number 50 and come up with the new set of forecast. Another way we can interact with the system, we can provide an override, is to not provide the absolute value, but kind of correct the model. Here, you can see the user come in and say, I don't know I don't want to specify the absolute value of the new trip, but I know the trip should be 5% more than what the AI produced. And we can also support this in the system, and we store this multiplier in the scenario rather than the absolute value. And what that gives you is, if there's a subsequent edit upstream, the multiplier will take effect once it gets to this flow. So we launched the system. This is the snapshot, various pieces of the snapshot stitched together, and you can see this is a very intuitive UI presented to the end user, where the black vertical line separate the historical metric versus the forecasted metric, and different color of series represent different scenario. And in any case, in any time along this process, you can just point to a graph I showed you before and say, I want to clone it and fork a separate scenario and continue my edit. It's very easy, very intuitive. And on the right-hand side, you can see this is the first stage of optimizing, generate the initial optimal spending situation. Is also surfaced through a UI. And we launched the system. People start to use it, and it's very important to monitor how people actually intervene with the system. So we have this real-time monitor of how the metrics are edited by human. On the left side, you can see there's a heat map of across different cities, how many cities are severely edited, how many cities are lightly edited. And it serves two purposes. One, we know the system isn't going out of whack. We know, if the entire thing turns red, we know probably something horrible goes on, system level outage and so on. And second, it provides feedback. If we want to send that back to the AI and retrain the model and iterate the model, we can send this as labels. So there's a lot of benefit after we launched this system and we realized this is the first time we bring on-demand optimization and forecast to the company. And we provide, rather than everyone using their own system and own ad hoc spreadsheet, we have a centralized storage and centralized way of interacting with the system. And different users can work on multiple scenarios together and they merge, pretty much like working on a repo with Git. You can fork, you can merge, and you can edit, you can submit to master, and so on. And we can gauge the quality of the model. We can run backtests automatically, or we can compare the effect with visuals. And this is a global scale solution because the engineer solution, the engineer elements, both the service as well as data store can be horizontally scaled. Now let's spend some time to dive into one blue box that I found particularly interesting and in fact most critical and complex, which is trip. Forecasting trip at Uber is similar to forecast how many cups of coffee is sold in Starbucks or how many nights in a hotel chain would be booked in a year. It's very important. It dominates the overall quality of our financial forecast. If we get the trip wrong, we get the entire thing wrong. It's also very complex. It's easy to get something. It's easy to get a heuristic. It's very, very hard to get accurate forecast because there are so many variables, there's so many factors. And we use highly customized algorithms. We use a lot of signal, and we compose models. And a lot of the engineering solution, a lot of the system concerns are tailored around supporting this single forecast. And I think Uber data science team has published more detailed articles and conference talk about the methodology, but I'll just briefly mention the two different classes of methodology of forecasting trip. The first is cohort model, where we partition the user base according to when they sign up, when they get engaged to the system, and we kind of model their behavior. We model the retention and trip of every active user, and we come up with the total trip. The second methodology is different. We directly model the trip as a time series, which is why it's called a black box model, in that we don't look into what composes the trip, and we use classic algorithms such as ARIMA X to deal with it. And we add important signal to improve accuracy, such as holiday, such as events, such as the incentive spending. These are all the important things. For example, if we know a city is going to host Olympics, how do we get the data from the last Olympic and train the model and try to figure out how Olympic will impact the growth of a trip? These are the interesting challenges that we have to deal with. And last, we deal with assembling technique because there is no single model that works. Usually we come up with a lot of algorithms and we try to compare them and combine them. And we use weighted average of multiple models, multiple candidate models to come up with the final forecast. And of course, it's a separate topic that goes into how we do assembling, but essentially we come up with a weight based on the quality from backtesting. So because of this, special complexity of this trip forecast, it adds dimension of computation complexity of the system. We tend to think forecasting time series is easy, right? You feed k number into the system, the number come up with k plus 1, k plus 2, k plus 3 numbers, and how hard could that be? And in fact, it's multiple dimensions added to the problem that make it much more computationally expensive. And here are all these dimensions. Obviously, we have all the markets. We have hundreds of cities that need to be trained individually. We also have candidate models or algorithms that I mentioned that participate in the final forecast. We can have 10 models. We can have as many as 100 flavor of models that need to be experimented. And then the third dimension is we also gauge the quality by backtesting the model using different windows. So if a city is 5-year-old, then there's 60 months. If we do monthly cadence, then there's 60 backtesting, technically a 60 backtesting window we can use. And if you compose the 3 dimensions together, it's very, very expensive to exhaust the space. Even if your primitive training take only 1 second, if you want to do all the 3 dimensions, it can take hours in proper infrastructure or even days. And usually what we do is when we collapse in 1 dimension, the problem becomes much easier and manageable. For example, as we listed here, we can collapse the market dimension. We can do a single city, and we can run the exhaustive ensemble model. And here you can see every row is a candidate algorithm, and every column is a backtesting window. And we collect the error of each candidate in each test window and measure their error. And every green box marks a winner in that window, and we just score the candidates. And whoever scores highest is used. But if you do this, you have to scale it to the 3rd dimension, which is all the cities, right? Or you can collapse in the candidate dimension and do all the cities a single model, and you have a very comprehensive view of its quality. And here, every row is a city, every column becomes a testing window, and you can know in very detail how the algorithm is performing, right? As the testing window becomes longer, the quality decreases a lot. Or you can collapse the 3rd dimension. You can statically select model without doing comprehensive backtesting. That's another approach. And to summarize, whatever platform we build, our goal is to support all the 3 dimensions together, all the cities, comprehensive testing, and ensemble that involves multiple candidate models and algorithms. It's a great challenge to the infrastructure and the platform. So I want to highlight some of the ongoing work that we're doing. The number 1 is to support new forecasting models. We have a limited set of models our data scientists are working on, but we have much more in the R&D phase that we want to bring in to production, and they pose new challenges to the platform. For example, if we want to train a model that's based on the user level metric, then we need to have a much larger scale training platform. If we want to apply deep learning technology to do time series forecasts or other forecasts, then we need to be able to schedule conventional machine learning workload together with deep learning workload. And third, we have a lot of external third-party data about holiday, events, we know about weather, and how do we incorporate them to further improve the accuracy of the decision? These are all the new challenges. And second, we want to generate financial insight. We want to come from generating the initial recommendation to continuously generating recommendations. Once we figure out something goes off, we want to rerun the analysis and automatically come up with the recommendation on what to do to our company's leader. And we recommend reallocation of the budget, correction of spending, pointing out inefficiency or bottleneck in the business. And last but not least, we want to build a federated intelligence system in Uber. For example, there's a lot of teams in Uber that handles forecasting for different purposes. Some teams forecast in short term in order to do optimal pricing. They want to decide the price for a trip. They have to have accurate forecast, but short-term forecast. The infrastructure team want to forecast in order to do capacity planning. And the finance team want to do forecast to set financial strategy. And how do we build a federated system so that we can leverage the intelligence of each other? And these are great challenges to all of us. And I think this concludes my talk. We want to go from machine-assisted human-making decision in financial intelligence to human-assisted machine-making decision in financial intelligence. And this is our ongoing work. Thank you very much.
Thank you, George. Okay, so we've got some questions for you, which is wonderful. So, first one. What's the most relevant problem Uber wants to solve with machine learning?
So, there's hundreds of application domains inside Uber for machine learning. I wouldn't exhaust all of it, but I'll just give a few typical examples. Forecasting is definitely a big problem in itself, and we use machine learning almost exclusively to do forecasting. And we have a spectrum of forecasting problem ranging from hourly forecast of demand, supply, to strategic forecast, which is the focus of my talk. And also, interesting problem is we deal with fraudulent users, right? We deal with risk of the system, and we use machine learning extensively to figure out how do we classify a user, how do we classify transactions so that we can understand what the risk is in the system, we can identify the fraud users.
Okay, great. So, do you use any machine learning stroke data science tools to analyze the media coverage on Uber to improve the strategic planning?
That's a wonderful question. I believe we should, but we have not used that yet. It's certainly an interesting direction, and we have discussion around it.
Okay. So, how can you take into consideration the service bans, like it happened lately in a few cities, London, almost, nearly, basically the market shrinkage regarding strategic planning?
That's a great question. So I think I have a slide that addresses the elasticity, the call for elasticity in the system, and this is the birth of the workload that I was referring to. Whether it's a service ban or it could be launching a city, it could be a sudden change in policy, it could be a sudden change in the strategy. But the way we take that into consideration is we have to adjust the forecast, we have to adjust the plan, and we have to rerun all the intelligence, basically, with this new change. Okay. So typically it's an on-demand process because no one can forecast these things.
So why is Uber even, it's late in the day, why is Uber not using Hadoop technologies for online forecasting as well?
I don't believe there's fundamental barrier, but because we use certain framework in Uber core infrastructure, we use Hadoop primarily in the offline flow. In the online forecasting, we use Spark, Cassandra, and those low latency things. But I could be wrong. There could be other teams that use Hadoop indeed to do online forecasting that I'm not aware of.
Okay. So how comfortable are your colleagues in finance with using this black box forecasting approach?
Great question. The same question can be asked for any AI, right? Because we're not forecasting for fun. We're forecasting for serious business need. And this is the number one question we should ask even before coming up with the strategy, right? Is there a way we can gain confidence? And the way to do it is to come up with the comprehensive backtesting technology and continuous monitoring technology so that, before we apply the model, we know it's good for the past. And after we apply the model, we know once it's no longer good for the future, we get notified. Okay,
final question. Will you stop switching between MySQL and PostgreSQL? I've never heard of this last one, I have to be honest. But anyway, go ahead.
We use neither in our architecture, but sounds like we should stop switching.
Okay, great. Actually, I'm going to throw in one last question, because this one's kind of been pushed down a few times. Yeah. But what concrete tools, software do you use in your stack?
Yeah, so our stack is a combination of open source frameworks such as Spark, Hadoop, Hive, Presto, and the in-house solutions such as microservice, the UI, as well as the pipeline, the data pipeline. I believe there's a lot of opportunity for us to further adopt open source framework, but again, it's just we are operating within certain scope of Uber infrastructure.
Okay, great. George, thank you so much for your time. Thank you for your speech and for answering questions. Let's give him a clap. And before you go, we have something for you. This is George. Okay, thank you. Have a great afternoon.